Okay. Good afternoon. Yeah, the attendance sheet is open, so you can go ahead and mark your attendance.
Good
Today we are
afternoon, Doctor.
yes.
Tomorrow will be the quiz, right?
The quiz will be on Tuesday.
Tuesday?
Tuesday. Yeah.
Okay.
Yeah. So today we are going to begin our next chapter. It is about uh, kinetic energy and work. The main theme of this will be to discuss energies, to discuss work, and combine the work and energies and show that the work and energy are essentially the same thing. This is another step just after the force introduction of the force into the motion. We said that when we apply a force, we can accelerate the object. So if there was a car which was sitting and I push the car, I'm able to produce some motion in the car. So what did I do actually? I transfer some energy into the car and the car as a result is moving. Okay, so force is the connection between me and the car. I'm able to transfer my energy to the car. Okay, and vice versa. If the car was coming and I was trying to stop it, then the car is trying to transfer its energy to me via its force. So this will be the connection which we will be bringing between energy. What is energy? Energy is a scalar quantity associated with the state or condition of one or more objects, such as kinetic energy and potential energy. We know that the kinetic energy is a form of energy which is related to motion, and potential energy is the form of energy which is associated with a state, such as if a car was at rest, you say it has zero kinetic energy. If the car was in motion, you say it has some energy, which is some kinetic energy there. Another case is that whenever we are talking about potential energy, so my marker, if it was landing on the, if it was lying on the floor, I say with respect to the floor, this marker has zero energy. But if I raised it up and lit it here, okay, on top of this whiteboard, I am putting it here, just because of the state, since it is moved from the floor to the top of this whiteboard, just the position of this has changed. Due to its position, the energy got stored in it. Okay, and that energy is called potential energy. Whenever I want to reuse this potential energy, I will just let it go and it will start to drop back towards the earth. Okay, and it will be able to produce some dent in the earth or something like that. I'll produce some sound or heat. So all different form of energies. There are different characteristics of energy. Energy is a form of the energy can be transferred from one form to another. For example, you have cells, batteries in your cell phone. You are charging your cell phone from the electricity, right? So then you are able to produce some different form of energies out of that stored battery. Like you can produce heat just because when you are operating your cell phone, it gets heat. Okay, so heat is one form of energy getting out of your cell phone. Another form of energy is the sound. If you are listening to music, you are producing different kinds of energy and you are vibrating different surfaces, right? So that's another kind of energy. So whenever you are thinking about the electricity, how electricity was made at the initial stage, then you also say that it was from the petroleum, right? So from the petroleum, the energy was the electricity in Saudi Arabia is usually the main source. So it was made from the petroleum. Petroleum is one form of energy, and now the electricity is a different form of energy. Okay. Another thing is the total energy of the system and its surrounding is always remain the same. It all remains constant or remains conserved. All different ways of words we will be using, either conserved or constant or remain the same. All these things mean actually the same thing. Okay. So you may have realized the lecture theme today, because I'm moving more into the introduction parts of the energy, introduction part of the kinetic energy, and introduction part of the work. I will be introducing these things we'll be doing a little bit problems, but I just want to build your background on these three things. Once you have the grasp on these three things, we will be going into a little more challenging stuff. Kinetic energy is, as it was introduced at the high school level, the kinetic energy is written as kinetic energy is half mv square. Okay, if you look at this, half is a constant. M is the mass of the object which you are trying to accelerate or move. So let's say in that example, it is a car, mass of the car, and v is the speed of the car. So it is, strictly speaking, it is just related to the speed, because most of the objects we are dealing with in our everyday life, it has some mass. So if the object was at rest, velocity will be zero. Therefore, the kinetic energy is zero. And if it was a non-zero, velocity was a non-zero value, then kinetic energy should also be there, no matter what. It should also not be equal to zero. Okay, it's just related to the motion state of the object. Okay. Can someone tell, just looking at this formula, can someone tell what will be the unit of kinetic energy?
Newton multiplied by second.
That is a later stage. We will be introducing that later on. Just looking at this one, this formula, what will be the unit?
Kilogram times meter per second.
Yeah, kilogram meter per second, and then it is squared. So when we take it out of the square term, then it will be kilogram meter square per second square. When the student said that it is Newton per meter, he is right, because when we are putting this, let's write this kilogram meter per second square and remove 1 meter to the right side. Kilogram is the unit of mass. Meter per second square is the unit of acceleration. So meter times acceleration, kilogram times acceleration is the force, right? And meter is again the distance. So here, Newton meter is the unit.
Is
So
that
what is that?
joule?
Yeah. Newton meter, we are also calling it joule, or we are also calling this kilogram meter square per second square is also joule. So joule is the SI in the short words for that, for the energy or the work, both of them. But how it is derived, always remember the kinetic energy formula, so that you can break down joule into the subunits like kilogram meter square per second square. Let me do this problem a little quick. Assume 2 locomotives at rest at the opposite end of a 6.4 kilometer long track. Each locomotive weighs 1.2 times 10 to the power 6 Newton, and it is accelerated. Its acceleration was a constant, and that is 0.26 meter per second square. What was the total kinetic energy of the 2 locomotives just before their collision? Okay, let's say there are 2 locomotives at the end of the track, and both of them are coming and hitting each other. So if I tell you that there are the track from here, from the train A to the train B, the total track is 6.4 kilometer. So if both of them were has the same mass and accelerated by the same amount, everything is the same. So how much distance each of the locomotive will cover?
3.2.
3.2, because the total distance between them is 6.4. So 3.2 will be the distance that they will cover. So 3.2 on this side, 3.2 on this side. Okay. Now we want to know the total kinetic energy. So we know there is a train A and train B. So kinetic energy associated with A and kinetic energy associated with B. So if I'm looking at the total kinetic energy, it will be the sum of the 2 energies. Kinetic energy is equal to kinetic energy. I'm just more got used to writing kinetic energy only K rather than KE. So I will be switching to that notation a bit quick, but just at the beginning, I want you to learn how this thing is coming out. Okay, kinetic energy A and kinetic energy B. Since two of the locomotives have the same mass and everything remains the same, so therefore we can say that at the end, both of them will cover the same amount of distance, and also they will have the same final speed. So that this kinetic energy A and B are both the same thing. So you can just write this as a kinetic energy of any one of them, either A or B. We also know that this kinetic energy is half mv square. So if you look at the problem statement, what we can see that mass, we can get that from the weight, but the velocity, we don't know it. How can we determine that?
By the motion equation.
Exactly, by the motion equation. So we know the distance here. Each of them covers 3.2. We know the acceleration, constant acceleration there. So
What's
we can
v?
use v square minus v naught square equal to 2ad. Since both of them are going from the rest, so v naught square is 0 for them. And we will be taking the square root of this side just to get this final speed, okay? Either getting the square root or no need to get square root, because at the end, we just need v square, which is right there, okay? So 2 cancels out. Mass is the weight, which is 1.2 times 10 to the power 6 divided by 9.8. It will give us the mass, because mass is equal to mg, weight is equal to mg. And then for the v square, we can put 2 times, the acceleration is 0.26, and the distance is 3.2 kilometers, so times 10 to the power 3 meter. Everything, since everything is known, whatever we get from it, that will be the total energy of the system. Any quick question here? Okay. Now, I'm introducing the work a little bit. What is work? Work, as I said, work is energy transferred to or from an object by means of the force acting on the object. So suppose that there was a car, it was at rest, and I'm applying my force to it, okay? So the car initially has zero kinetic energy because the car was at rest. Afterward, when I'm applying some force, I do work on the car, I did some work on the car, and the car as a result moves. So what I did actually, I transferred some part of my energy, which was stored in my muscles in the form of chemical energy. I transferred that into the car, and we are seeing that energy now in the form of kinetic energy. So how did I transfer? Just because of the force, because I was applying the force on the car and the car went as a result, okay? So work is energy transferred to or from an object by means of a force acting on the object. Whenever we talk about the work will be done can be considered either positive work, or it can be also considered negative work. How work can be positive? When I give you the example that there was a car at rest and I did some work and the car moved as a result, this work was positive because I transfer energy to the car. But if suppose that the car was in neutral and it was coming down the incline, so it already has some kinetic energy, and now I'm working on it just to stop it. So as a result, you may be seeing that if I was able to stop the car, what I actually did, I took the kinetic energy from the car and transferred that to me. Okay, so at the end, we come to a stop. So the car did some work on me, okay, which will be also considered the work done by the car. Work done by the car. And for the car, it is considered negative because the energy from the car is transferred to me. So whenever energy is transferred to the object, like the car, it will be positive. If the energy is transferred out of the object from the car, in this case, that will be considered negative. Another example is like in terms of the potential energy, there is this marker. It was initially laying on the ground, and I raised it up to the top of this platform right here. So what I did some work on it, and the energy is now stored in the form of potential energy in the marker. Okay, so I did some work on it, and the work is positive because the energy is stored in the marker now. But if I start to hold this and taking it controllably in my hand back to the ground, okay? Now I'm holding it and moving it down to the ground. What I actually do, the marker goes down, but it does some work on me, okay? Because the kinetic energy is going to be transferred from the marker back to me, okay? So that will be considered negative work. Again, from this work energy principle, the Newton meter we already introduced in the previous slide. So joule or kilogram meter square per second square or Newton meter, all these are different alternative units for the energy or the work. Again, one more example about the positive work and negative work, and I'm introducing some language in this slide. So try to understand this first. By speeding up an object or slowing it down by applying a force, you are changing the kinetic energy of the object. If you speed up an object, you transfer energy to the object. So the work is said to be done on the object, work done on the object, and that is considered positive work. If you slow down an object, you transfer energy from the object. The work is said to be done by the object, and that is considered negative work. So work done on the system and work done by the system. By the system, that work will be considered negative. On the system, that work will be considered positive. So I'm trying to formulate this work energy principle now. And here, as you are seeing in the slide, that there is some force that is acting on an object, and that object is a point object or bead. So this is a one-dimensional motion. Object is lying in one dimension, okay? Like this. This is one dimension. Now, suppose that you have a point mass right here, and you applied a force, like you tied a string or something to it and you are pulling it out. So something like that, this is the direction of your force that you are actually applying on it. But as a result, the object only slides on this floor. It doesn't go up. It just slides along the floor. So the direction of the motion of the bead is just this direction. So the displacement it has covered under the influence of the applied force. Now, by definition of the work is said to be done if under the influence of the force, the object covers a displacement in the direction of the force. So if I tell you that this object goes along the horizontal floor, which component of the force is actually acting here?
X component.
X component is actually acting here. So X component is this one, and the Y component is this one. The Y component does not work. If it worked, then it will be actually lifting the bead upward. But it is not lifted up. It is just sliding along the plane. So therefore, the component of the force that acts here is the X component. So here I'm writing this, that the Fx component times d. And we know that this Fx, it can be written as, if this was an angle, we know that this is F cosine theta, and this is F sine theta. I can write this as F cosine theta times d. Do you guys remember that the formula A dot B is equal to AB cosine theta for the vector product? This was the scalar product, right? A dot B times AB cosine theta. So here you have F and D. You can rearrange the cosine theta just to see, look the equation something like close to that, if you got confused about that. So you have FD cosine theta. Now, by just definition of the vector multiplications, I can write this in the form of the work, the vector notation. So if it will be the F vector times D vector. D vector is the displacement and F is the total force. Whenever you look for that, it will be again back the sine theta, which is as a result is the X component of the force. Okay, so this is the work definition now. And if you ever wonder in the chapter, that was chapter 2, probably chapter 3. If you ever wonder what is the implication of the dot product when we have A dot B equal to AB cosine theta, the implication started to appear here. The work is actually F dot D, and which is the FD cosine theta. And when you have cosine theta, based on that, you can actually declare what will be the behavior of the work. If the angle between the force and the displacement is 0, then you will do more work. If you just, instead of incline, this force was applied just straight along this direction, so the angle between D and the force will be 0, you will do more work. If the angle between the work, the force, and the displacement was opposite, then you will never be able to do any work just because the cosine 90 is 0. So you started to see the applications of that now. Just try to remember this formula, which is the FD cosine theta, or F dot D in the vector form, and then we will keep using that. There is another application I want to bring, since we are using the force, and we are saying the force is the main agent, which actually causing the interaction between the two objects, like between me and the car in that example. So there was the force through which I was interacting with the car, right? So this is the force and this is the displacement covered. You guys remember that for the force there was another equation, a theorem, and that theorem was the linear superposition principle. When we said that, recall that example, in that I given you an example of a car, like you're asking 2 friends, 3 friends, or 4 friends, and all four friends are coming and they're pushing on the car. So the force of the friend 1 plus 2 plus 3 plus 4, all friends' forces will be added up. And as a result, you get more force. That was the linear superposition principle. Here, instead of seeing one force, if you say that I'm talking about the net force, okay, just changing this much in the formula, not more. If I'm saying that instead of the single force, I'm talking about the net force, then the net force will come from different forces, right? In that example, it will be the sum of the 4 friends' forces. 2 plus F3 plus F4. This net force is the sum of the 4 forces. All I'm going to do now is to take the dot product with the net force, F net times D. I will be just taking on the right side the dot product as well with each term. Like you are multiplying with the 2, so you are multiplying everything with the 2, right? Like in that form. So F2 times D plus F3 times 3 plus F4 times D. Okay? Everything like that. Just nothing changed. When you are seeing this, F1.D, F2.D, F3.D, and F4.D, what do you see about this? It is the work done by the force 1, it is the work done by force 2, it is the work done by force 3, and so on and so forth. Okay? So at the end, I can write this, the total work done, or the net work done, is equal to the work done by 1, the work done by 2, the work done by 3, and the work done by 4. So this is, since I just included only limited number of forces, and therefore I have only limited number of the work done by those forces. But if there were n number of forces, then all you do is that it will begin from W1 and go up to Wn. In the summation form, you are writing it like this. The I, you are representing work I, and I begins from 1 and it goes up to n. So this will be your summation form. So now, in this example, if you have n number of friends, since we can count friend number 1, friend number 2, they are discrete, right? They are separate, like I can recognize friend number 1 from friend number 2. So in their case, I can use the summation with no problem. But what if I was having a set of saints, okay? And saint, there are many number of saints, like millions of saints are in one box, okay? And if all saints are acting on it, so as compared to the person, the saints forces will be a lot, million times. So million times summing each of them and adding at the end, it is extremely complex. So this summation sign at the end, for that kind of fine boundaries, can turn into the integration sign, and that will be W, like a dW, differential work, like that. But this is not, at the moment, we are not dealing with that. I will introduce the integration sign later on. So, since we know the work and we know the kinetic energy, we are going to combine both of them, okay? How the kinetic energy and the work, both of them are actually coming out to be the same thing, okay? And as you are seeing that if I'm doing work on the car, I'm able to accelerate it. So it will move with some speed if it was initially at rest, or I can increase its speed. If it was initially moving and I apply my force, I can increase the speed of the car. On the other hand, if it was moving, I'm applying my force, doing work on the car, and I can stop it. Okay, so something like that all the times can happen. So what I'm trying to do now is to make a connection between the two. And you will see that this connection we already had explored in chapter 4, sorry. In chapter 4, we had been talking about it, but that was not explicit, a little bit potential, like implied. Okay, recall that when we were solving the previous problem for the locomotives, there was an equation that we had used. And that equation was 2a d is equal to v square minus v naught square. This is the equation of motion that we had derived for the constant acceleration case, right?
Yes.
Yeah, what I'm doing that, I will multiply both sides with the mass and divide both sides with 2, by 2. So it will be MAD, and it will be half MV square minus half MV naught square, okay? What is MA?
Force.
It is a force. So I'm writing instead of MA, I'm writing force. And what is the equation of the FD? What it tells us? It is the work. And this equation is half mv square is kinetic energy. So this is the final kinetic energy, and this is the initial kinetic energy. So just from the equation of motion, we can tell that if change in the kinetic energy is happening, that will be due to the work, right? Either the work is done or on the system or by the system. So you can see either the initial kinetic energy will be more or the final kinetic energy will be more. And accordingly, the sign of the work will become positive or negative based on that. So this is the work energy principle. It comes from the equation of motion. But we should be a little bit careful here when we are applying all these all these formulas. First of all, you know that this equation was derived specifically for the constant acceleration case. So therefore, the work energy principle is in this form. As we are using it without integration, then that will be only applied to the constant acceleration situation. That's one thing. Second is that you are not considering any non-rigid objects. All the rigid objects means if I'm moving this this marker, I know that with the distance between the tip and the base will remain the same. So this is a kind of rigid object. I can move this, right? But if it was something like a sponge, like this, and along that motion, as it moves, and it was squeezing and kind of the distance between the particles is decreasing, then it will not be the case. Okay, like this, you see the prayer rug, as it is moving, and if it was kind of changing its shape, then what will be the situation that the front particles and the back particles will not cover the same distance. Therefore, this formula cannot be applied to any soft object, non-rigid object. Here's a checkpoint, guys. A particle moves along an x-axis. Does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity change from -3 meter per second square to -2 meter per second square? This is the work energy formula as you are seeing on the blackboard here, on the whiteboard, and just answer the first one. What do you think? Should it increase or decrease?
Increase.
Decrease.
Always make sure that when you are just, I'm trying to solve one of them, m, the final speed you have -2, and it is under the square term. So it doesn't matter whether it is 2 or -2. And similarly, for the second one, it is -3 square. So initially, the kinetic energy was more. Just eliminate the negative sign. Initially, the kinetic energy was more. Later on, the kinetic energy is less. Okay? So the kinetic energy has decreased in this process. How about from -2 to 2?
The same.
It remains the same. Again, the plus minus sign does not matter because it is under the square term. So therefore, -2 and +2 both are the same thing. In each situation, is the work done on the particle positive, negative, or 0? So how about in the first case? In this first case, is the work done on the particle positive or negative?
Negative.
Negative.
Negative, because the second term is more, the first term is less. Therefore, we will get the negative sign out of this problem, and the work will be negative. And how about in the second case?
It's 0.
Zero work. Okay. Let me try to solve this problem, guys.
Doctor, I have questions.
Yes.
So the work is scalar.
Yes.
Okay. Yes.
Yeah, because the dot product is there, like F dot D. If it was F cross D, then that will be a vector quantity.
Me too, teacher. I have a question.
Yes.
What is the benefit of the work in real life? Because we can use the Newton laws instead of work.
What is that? I just lost the first
What is
part.
the benefit of the work in real life or
Okay.
day life?
Yeah. So the work is, without work, we will not be here, right? So we are doing work, and that's why we are here, and we are doing something. The work, the definition of the work is a little bit different than the work definition that we use in our everyday life. If your mom tells you to go and study, you go and sit on your table, right? You sit on your table for multiple hours, and you keep reading that, but you are not doing any work. The influence of your force, you are not moving things in some direction. So in that case, you are doing zero work based on the definition of the physics, okay? But if you are able to come out and have applied some force on it, and you are moving it under the applied force, then you are doing some work. So in everyday life, for example, you are running your car, there are gasolines in your fuel tank, and then from the gasoline that goes into the engine. The engine is injecting some fuel into the engine, and it is burning that. And you have compressors. The compressor compresses the gas it produced inside the engine, and due to that, it produces a little bit torque, and as a result, your car moves either forward or backward, whichever direction you want, right? So there is the work coming from the energy, and that is how the energy is transferred from one farm to another farm. Either the car broken for some reason, and you are towing that car. You hook up your car to that next car. You are pulling it along the direction, along the road from one point to another point. So you are doing some work because your car is pulling the next car by some force, and it covers some distance. Therefore, there is work. So work is all the time there, no matter what. If we eat some food, we are bringing something into our mouth or water. We are doing some work because we are lifting up some mass in some direction. We are doing work. So work is all the time there. Yes.
Thank you.
Yeah. So in this problem, there are two spies, 001 spy and 002 spies. The 001 spy is pushing the cart, the safe, and the 002 spy, it is pulling the safe. So you know that when this guy is pushing the car, the safe, the direction of the application of his force will be this direction. And since he is pulling it, he is applying the force in this direction, right? So these are the two forces these two guys are applying. And as a result, the object, this safe, is only moving along this direction. It is not lifted up from the ground, but it is rather going sliding on the top of the surface. So what we need to do is to understand how much work is done by SPY 001 and SPY 002 under the application of these forces with that specific angles. So let me solve them here. Okay. We know that this when we are designing the dividing these components of the forces, as I sketch the lines, you can see a little more details of this. You see that this is the x direction in which the object is going. So we know that the force F1 and F2, both of them are with the angle 30 and 40 respectively. So what we are going to do is to take the components of the force along the direction of the displacement. That will be F1 cosine theta, which will be along this direction, and also the F2 cosine theta, which will be also in the same direction. Okay, so what we are just going to do that and then determine the net work. So work done by the first guy, that is F1 cosine theta 1, and the distance he has covered, this much. So what we need to look for is the force. The force he applied is how much? It is
12.
12 Newton. And the angle that he is making is 30. And the distance by which they have moved the object is
8.5.
8.5 meter. Okay, 8.5 meter. So this one will give us the work for the first guy. And then for the second guy, we can do the same. It will be F2 cosine theta 2 times D. It will be again, the F2 is 10 cosine, and this angle is 40, and this displacement is 8.5 meter. So this one will give us the second work. Since both of the work are done on the object, because both the spy number 1 and spy number 2, both of them are transferring their into the box, right? So in that case, both work are positive. So I'm not changing the sign of any of the work, but the total work is going to be W1 plus W2. And if the two works, that is their solution for it, which is 153. If you add both of the work, calculate them and add them. So 153 joule, that's the net work. Now, in this case, during the displacement, what is the work done by the gravitational force on the safe, and also what is the work done by the normal force on the safe? So if the object was going in this direction along the x-axis, okay, and we look for the components of the gravitational force along the x-axis, how much is the component of the gravitational force along x-axis?
0.
0, because the cosine theta between this and either you can go by the components like fg cosine theta, f g x. You can say that if it is fg cosine 90, for the lower one it is minus 90, and since either for the plus 90 or the minus 90, in both cases the cosine is 0, therefore we are getting this component 0. Either going in from the components like this, or just saying the angle between the displacement and the force is 90, therefore the work done by the gravitational force is 0. The same is true for the normal force. The angle between the normal force and the displacement is 90, the work will be 0. The detail is here, okay? The safe is initially stationary. What is its final speed at the end of the 8.5 meter displacement? So which theorem we should use here? What was the name of that theorem?
Work energy.
Work kinetic energy theorem we should use here. And we know that the work is equal to kinetic energy final minus kinetic energy initial. So it says that if the safe was initially stationary, so we know it is half mv naught square, so the initial kinetic energy is 0 for that. And at the end of the journey, how much is the kinetic energy? So we know it's just the total energy is equal to the final energy. So 153 joule is equal to the final energy, which is the half mv f square. Okay. In order to determine the final speed, you multiply both sides with 2 and divide by the mass of the safe. Okay. And you will be left with this. And at the end, you need to take the square root in order to get the final speed. So the mass of the safe is also known, by the way, in the previous case, which is 225 kilogram. Okay. So once you put that, it will give you the final speed. Everything is known. There is another problem related to that. This is strictly about the negative work. Let's try to understand the negative work, how that work is done. So in this one, during a storm, a crate of crepe is sliding across a slick, oily parking lot through a displacement d minus 3 I, while a steady wind pushes against the crate with a force which is also given in unit vector notation. The situation and coordinate x's are shown in this problem figure. How much work does this force do on the crate during the displacement? So if displacement is given to us in the unit vector notation, and also the force is given to us in the unit vector notation, can you tell what will be the easiest way to solve this problem?
3 times 2. Find the magnitude. And then multiply them together.
Okay. Yeah, that's one good approach, but I want a little bit easy way of approaching to it. Can other students comment on that?
The force on x and y axis.
Yeah. So since we know that the work is the dot product between the force and the displacement, we will directly take the dot product, F dot D, and that is the easiest way to approach to it. Though the other question, the student which he answered, it is also a logical approach. Yeah. So work is F dot D. And all you need to do is to put them in the unit vector notation. It is 2I. I'm not writing the Newton here. And this is minus 6J. We're taking the dot with minus 3I. And we have the Newton from here, meter from here, so it will be Newton meter then. Okay, whenever we take the dot product, so the dot product between I and I is positive. It is giving us a value, and I dot j or j dot I is 0. So the only term that will survive, it will be the first term. So 2 times 3 is 6, and there is plus and there is minus, so we get minus 6, okay? And I dot I is giving us 1. The second term is 0. Newton meter, or you can also say joule, minus 6 joule.
Yeah, we can
What is that?
think about this differently too,
Yeah.
which is my answer. 3 times 2 instantly, because the box isn't going up, so the j doesn't matter.
Yeah, exactly.
The only thing we care about is the force along the x-axis. So
That's a very good interpretation, because what we are trying to emphasize that the work will be done by the force if the force is able to move the object in its direction. So if the force was applied in whichever direction, the only component of the force we will be taking, that will be along the direction of the displacement. So the direction is along I, therefore only I we take. The j we don't consider it. Yes, that's a good answer, yes. And this is since you guys are seeing it is negative, because you can also see that initially if the object was coming down, let's say assume that the parking lot was a little bit inclined and it was the crate was itself coming down, but now the wind is coming on the opposite side. All it is doing, it is slowing down the crate. The crate is still going, but the wind is from the opposite side, therefore it would go with a little bit slow speed. Okay.
Doctor, I have a question.
Yeah.
Should we care about the friction when we want to find the work?
That's a very good question, and we are not, once again in this chapter we are not including the frictions. The friction will be included in chapter 8. Okay, so now we are guiding you just with the normal force, like similar to the chapter 5, in which we were not including the friction at all. But once we do that, it will be a little bit later on, because we want you to understand the first concepts of the force and later on apply those concepts to complex situations.
Okay, thank you, Doctor.
Okay. If the crane has a kinetic energy of 10 joule at the beginning of the displacement, what is its kinetic energy at the end of the displacement? So again, we are using the work energy theorem. We know the work is a minus 6J. That's what I'm holding on. And I will be saying that the work is equal to Kf minus Ki. And since they are saying at the beginning of the displacement, it means that they are giving us the initial kinetic energy. They are asking us what is the final kinetic energy. So the final kinetic energy from this equation will be W plus Ki. So the work is minus 6J, and the initial kinetic energy is 10J. So total will give us 4J. So that's the final kinetic energy for this case. Okay. At this point, I'm going to stop. I'm open to your questions. Next topic we will begin. It will be work done by gravitational forces. Okay, it will be a little bit more relatively going towards the potential energies. Yes. Do you have any question here?
Doctor.
Yes.
How come the work is negative in the previous example?
Yeah, because as I told you that the work if you look at the force, you see this is the force direction. So let's put in the components, this force in the components. You will be seeing one component force along this direction and another component along the y direction. Since this component, y component doesn't matter, but if you look at the angle between the displacement, which is this way, and the x component of the force, which is this way, so how much is between them?
180.
180. So if you just look at from the mathematical perspective, like f d cosine theta, and you put the cosine 180, you will get the negative in there. That is mathematics. From the physics perspective, as I said, suppose this crate was here initially, it itself was sliding down. Okay, it was sliding down with some speed. All the wind is happening, the wind is from the opposite side. Do you think that the crate will a little bit slow down?
Yes.
Okay, that's what that's what the negative energy, the negative work done means. If it was coming with some faster speed initially, so higher kinetic energy, if the negative work is done, it will slow down the object. You will be seeing the object kinetic energy a little less. So again, less kinetic energy minus more kinetic energy, you will get more negative here, right? That's why the negative work is seen.
Okay, so I can say that I can imagine if they are in the opposite direction, the displacement and the force.
Yeah,
I can imagine that the work will be negative.
if the yes, of course, like if you see that the force is applied in one direction and the displacement is covered in a different direction, like as you are seeing in this, that will be negative work. Imagine another situation like this. Suppose the car is coming towards you, and hopefully it's a little bit lighter car and not much high speed, right? So if it was coming towards you and you are trying to stop it, so the car initially has some kinetic energy. You are applying your force in the opposite direction, which is completely opposite to the direction of the motion of the car. So the displacement covered by the car during the application of the force and your force, both of them are in opposite direction. The angle between them is 180. And you are stopping it, so you are taking energy out of the car. Initially, the car has some kinetic energy. When you bring that to a stop, it will have zero kinetic energy. Right?
Right.
Okay. If you have any other question, it's fine. Otherwise, class time is over. You guys can leave.
Doctor,
Yes.
can you please open the attendance? I didn't do it at the beginning.
You didn't do it. When did you join?
12:10.
12:10. So 12:10, it was open. Okay. I will be opening it. The students who have already signed up, don't try to sign up.
It's me too, Doctor.
Oh.
Okay. I joined at the beginning at
Who are
12.
okay. How many students are there who didn't sign up? Just tell me, because I'm looking at the form later on, and there is one student who tells me, and later on I see there are 3 students who are signing up. Okay. Okay, do it now, and this will be the last time that I'm giving concession. All students have to do their attendance before 10 minutes after the class.
Doctor, tomorrow we will continue with the lecture.
Tomorrow?
Or we will have
I'm more inclined towards the lecture, because I feel that the students, if they don't have the know the material of the lecture, then they will not understand the problems in detail. So I will try to finish the lecture, conclude the chapter, and then do the recitation afterward.
Doctor?
Yes.
I want to ask about the homework that we just did, the homework on chapter 6.
Okay.
I got a wrong answer because I wrote a number so close from the answer key.
Okay.
I'm wondering if there any chance that you correct the grade for me.
Yeah, so send me your concern along with your ID and the section number. So I understand your concern. You write that.
Yeah,
And
I should send you my answer and the answer from the Wiley Plus.
whatever thing is easy. If you describe the situation that this was the situation, this is the problem number, I'm having the question regarding that, I will go and look at that.
Okay, thank you.
So, but send me your ID and the section number and the question number which you want me to look at.
Okay, thank you very much.
Yes, I'm guys having another class that is beginning now, so I'm leaving this session. Okay.